At Northrop Grumman, innovation isn't just an idea. It's a way of life. The value of performance. Northrop Grumman.
Okay, hello everybody. I'm Colin Adams. I teach at Williams College, but I'm also a knot theorist. I'm a mathematician that studies the mathematical theory of knots. And what I want to do today is tell you about knots and why anybody would want to study them and what the mathematical theory of knots really is. So I'm going to start by going all the way back to one of the first knots that anybody has ever talked about, and that's the Gordian knot. And this goes back to 333 BC. And the Gordian knot is this knot of which there is this legend about the knot, and what the legend says was, when Alexander, at the time Alexander was hoping to take over the world, the known world at that time, and when Alexander reached Gordium, he was seized with a longing to ascend to the Acropolis, where the palace of Gordius and his son Midas was situated, and to see Gordius's wagon and the knot of the wagon's yoke. Over and above this was a legend about the wagon, that anyone who untied the knot of the yoke would rule Asia. The knot was of cornel bark, and you could not see where it began or ended. Now that particular phrase is going to be key for us, as we'll see in just a second. But I will finish the story. Alexander was unable to find how to untie the knot, but unwilling to leave it tied in case this caused a disturbance among the masses. Some say that he struck it with his sword, cut the knot, and said it was now untied. But Aristobulus says that he took out the pole pin, a bolt driven right through the pole, holding the knot together, and so removed the yoke from the pole. So he cheated a little bit, but that's okay. We're not going to hold it against him. But in particular, this idea of having a knot where you cannot see where it begins or ends is really the essence of a mathematical knot. And so we're going to look at a knot in the following way. And I'm going to use this toy called the tangle to demonstrate. What you do is you take your string or your rope, you tie a knot in it, any kind of knot you want, and then you glue the two loose ends together, in this case by snapping the toy shut. So now I've trapped that knot on this particular toy. And I might spend the next 3 years trying to disentangle this, but in fact I will not succeed, because it is not the equivalent of what we would call the trivial knot or the unknot, which would just be an untied circle. And you'd like to have techniques for determining, if somebody hands you something like this, whether or not you could disentangle it. So that's the basic idea of knot theory, is this idea of can you disentangle a knot or not. So once we have this idea, we can start making tables of knots. And here you see a table, the beginning table of the knots. The very first knot there is the unknot or the trivial knot. Then comes the trefoil knot right next to it, the figure 8 right next to it. Those are 3 crossing and 4 crossing knots. And then these knots start going up in the table. No two of these knots that are pictured here could be rearranged, if they were made out of this toy, could be rearranged to any other one. These are all known to be distinct knots. Now, we can also do an operation on knots called composition of knots. And the idea of composition of knots is you take 2 knots, you cut them open, and then you glue them together to get a new knot. Okay, so that's called the composition of a knot. And the first question you might ask is the following. Can you take 2 different knots, compose them, and get the trivial knot? Okay, so I might take the knot over here. I'll use it on the copper-colored one here, and I've got a knot in there. Okay, and then I'm going to create a knot over here. I've got to do it just the right way. But I'm not cheating. This is really knotted over here. Okay. So I've got one knot over here, one knot over here. I'm going to hook them together. So I hook this one over here, and I have now composed this knot with this knot. And the question is this the trivial knot? So what I'm going to do is I'm going to pull this around here, pull this through here, go along like this. Whoops. I'm not cheating. Hang on. And pull this around. And the answer is no. Cannot be done. But it took mathematicians 30, 40 years to get to the point where they could actually prove that you can't do it. Now, you already knew this, because you know that when you pull an extension cord out of your closet and it's all tangled up, how often do you tie a second knot in the line and say, okay, this will undo it, right? So intuitively, you knew this. But it took people a long time to prove this. But now, once we have this idea of whether or not it is a composition of 2 knots or not, we can parallel what happens with the integers. So just like you can have a prime number, you can have a prime knot, a knot that is not the composition of 2 simpler knots. And just like we can have a composite number, we can also have a composite knot. Okay? Now, if we want to start trying to tabulate all the knots, what we're going to do is focus on the prime ones, since we know we can get the other ones by composing them. So we can start making tables of knots, and so here's a longer table of the knots going up, and you can start trying to figure out all these possibilities. Now, it's really hard to make these tables, and the reason it's hard is somebody gives you two of these knots. How do you decide that you could or could not rearrange one to look like the other? That turns out to be a very difficult thing to do. One of my favorite papers in all of mathematics is this one right here. And this one came out in 1998, and it's called, as you can see, the first 1,701,936 knots. And what happened was 3 different mathematicians actually working. One was out in California working with a team of high school students and using a supercomputer. The other 2 were out on the East Coast, and they both tabulated all the knots that you could draw with 16 crossings. So if you draw a picture and it has 16 places where the knot crosses itself, and then they could actually show that once you figured out which of those were equivalent and which of those weren't, they could figure out that this is the total number of knots that you get. Okay? Now, of course, by now, you're probably asking the question, well, that sounds kind of interesting, but why would anybody want to do this? Why do we care about the different knots that exist? And so I want to give you a couple of reasons that are actually very tangible. And let me start with DNA. Okay? Now, DNA is a very long, skinny molecule, and it has this double helix structure, but we're going to ignore that for a second. We're just going to think of it as a long, skinny molecule, and it's stuffed into the nucleus of a cell. It's been described as putting 200 kilometers of fishing line in a basketball. Okay? But it's not wound nicely. It's a huge mess. And yet it has to be able to do transcription, recombination, other functions in order for life to occur. So the question is, well, how does the DNA do that? Now, it turns out that there are molecules inside the nucleus of the cell, and what they do, these are called enzymes that come up to the DNA, takes one strand of DNA, takes the other strand of DNA, cuts the one open, pushes the other one through, and then glues the first one back together. That's called a crossing change in knot theory. Okay, so we're actually changing which knot it is, but there are these actual molecules inside the nucleus of the cell that are doing that all the time. So it becomes interesting. Actually, there's a chemotherapy drug that has been developed based on this called doxorubicin that prevents the enzymes from acting and therefore prevents the defective DNA coming from a tumor from recreating itself. So this has actually had direct applications for cancer research. So in particular, you can now define this idea of what's called the unknotting number of a knot. And the unknotting number of a knot is the least number of crossings that you have to change in any picture of the knot to turn it into the trivial knot. Okay? So here's a knot, one of my favorite knots, the 7-4 knot. And the question is, how many crossings do you think you would have to change in order to turn that into the trivial knot? What do you think? How many crossings would we have to change? What do you think? 3? Okay, we're going to try this, and I need a whole lot of volunteers, and we got to do it quickly because I don't have much time. So I would like 16 volunteers total. You're in, 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 you're in. Come on up here. I want 2 groups of 8. And what we're going to do is we are going to create this knot out of people. And here's what you're going to do. In this group, I need 4 people in the center. Okay, so 4 people in the center, 2 facing each other this way, and then you're going to be back to him, and you're going to be facing her. Okay? And over in this group, I want you guys to set yourself up the same way. So I want 4 people in the middle, back to back, just like that. Then I need 2 people on the end here. Okay, so you 2 are right here. You stand right here, here and here, a little bit closer, right over here, and over here. Good, right there and there. Good, good, good. And you guys, come on over here. You 2. And then I want you guys over here to fill in, just like we're doing here. You guys come on the end right here, next to each other. 1 and 2. So now, in order to turn this into the trivial knot, what we do is we switch 2 crossings, there and there, okay? If we switch those 2 crossings, then in theory we should be able to unknot. And so I'm going to switch you, but don't do anything until I say go, okay? And this is going to be interesting. So we're going to switch this crossing here, okay, and this crossing here. So you're going to probably want to go down when we start so he can get across, okay? And the trick's going to be don't let go, guys. As soon as you get started, don't let go of your hands and try to disentangle. And here, we're going to switch this one to here. That looks good. And this one, I think, here. Okay. When I say go, I want you to try to disentangle without letting go of your hands. We're going to have a race, and we're going to see who does it first. You ready? On your mark, get set. Go. Oh, you guys are good. Keep going, keep going, keep going, keep going. Turn around, turn around. Good job, guys. Good, all right, thank you, folks. Very good job. Okay, thank you, guys. Very good, you guys did good. Okay, so one application to knot theory is DNA. Let me show you another application, which is very interesting. Think about making a molecule by gluing a sequence of atoms together end to end until they glue to the other end and they form a circle. So benzene is a very famous example of a molecule that bites its own tail like that. Now imagine taking that same sequence of atoms, bonded in exactly the same order, cut it open, turn it, tie it into a knot, and glue the ends together. You now have a molecule that has completely different properties from the one that you started with. And as we said, if you just look at knots of 16 crossings or less, there's over 1,700,000 different knots of 16 crossings or less, which means you could make over 1,700,000 different substances with one sequence of atoms bonded in one particular order. So biochemists are and synthetic chemists are very excited about this idea. Here is an example of a knotted molecule. This particular molecule right here is a knotted molecule that was one of the first ones synthesized in about the year 2000. And chemists are trying to figure out, and biochemists are trying to figure out, how can you synthesize these knotted molecules? How do you tie a knot on the molecular level? And that turns out to be a tricky question. Now, a related question to this is, if you think about bonds as being straight lines, then you kind of wonder, well, how many sticks does it take to make a knot, which would correspond to how many atoms you would need to make a knotted molecule. So we want to ask that question. So we're going to look at stick knots right now, and we want to ask the question, how many sticks do you need glued end to end in order to make a knot? Do you think I can make a knot with 3 sticks? What's going to be the problem with 3 sticks? It'll just form a triangle, right? And a triangle is not going to be knotted, okay? So 3 sticks is not going to be enough. Do you think I can do it with 4 sticks? Yeah, 4, think about what a picture with 4 sticks would look like, okay? With 4 sticks, it would look like that if the sticks crossed, or it could be a square, right? So in either case, it's not going to have enough crossings in order to make a knot. So 4 sticks is not enough. What about 5 sticks? Well, you guys can try it, because everybody here has 5 sticks on them, namely your lower arm, your upper arm, your other lower arm, your other upper arm, and across here. Can you clasp your hands in a way in order to make an actual knot out of it? What do you think? Don't hurt yourself. We don't have insurance to cover that. It's kind of hard, isn't it? It looks kind of hard, okay? So what about this idea? What if we take one more stick? Whoops, so I'm going to take one more stick right here. I'm going to give you a stick. And I need a volunteer from the front row right here. Who's interested? Okay, come on up. Okay, and why don't you come on up on the stage? And I'm going to give you one extra stick, and I'm going to let you make a knot out of the 5 sticks that you already had and the one extra stick, but I'm going to help you, okay? So here's what we're going to do. We're going to cross your arms really tight there. We're going to stick the stick, whoops, I'll try not to hurt you. Stick the stick through there. Okay, now you hold this part with that hand, hold this part with that hand, and there it is, a 6-stick knot made with 6 sticks. Okay, there you go. Good job. Thank you very much. Nice job. Okay? So it turns out that you can, in fact, make a non-trivial knot with 6 sticks. This is a 6-stick trefoil knot that you see right here. You can actually do it with 6 sticks. But it's a really interesting question how many sticks it takes to make any given knot. So what if I take a composition of 2 trefoils? Take 6 sticks to make 1 trefoil. How many sticks do you think it'll take to make 2 trefoils put together like that? What do you think? 10 or 11? Okay, because it took 6 to make 1. You'd expect it would take a fair amount to make, a double. It turns out that you can do it in 8. You only need 2 extra sticks for that whole other knot, which is very surprising that that's true. In fact, it turns out, and this is work I did with students, small is our summer program, so this was done with students, that the stick number of a collection of n trefoils in a row is just 4 plus 2n. Every additional knot only requires 2 more sticks each time, okay? So that's really kind of an amazing fact. Here's another thing that was work that I did with students. This was 2 summers ago. I had a bunch of students working with me. And we showed that every knot can be drawn in a picture that looks like this. And that was not known. For 100 years of knot theory, nobody realized that before. And it's really kind of cool that you get this sort of petal picture of a knot that looks like that. And then the subsequent summer, I had another group of students. And they actually showed that the unknotting number that we talked about before is related to the petal number, which is the number of petals in the petal diagram. So it turns out that all these things end up being related, as it turns out in the end. OK, so what's left to do? In knot theory, in mathematical knot theory, what sort of things do we not know? Well, it's pretty amazing what we don't know. We don't know the stick numbers for these very simple knots called the 2 braids. So these are knots where you just have 2 strands braided around each other, going around. We don't know what the stick number is. I can tell you the stick number of the first one and the second one, but I can't tell you the stick number of the nth one. I don't know what it is. Nobody else knows what it is. It's still open. Okay? I showed you that if we composed a bunch of trefoils, we know what the stick number is. But if I change just one of those to a figure-8 knot, I don't know what the stick number is. It turns out to be hard. I can build one with a certain number of sticks, but how do I know I couldn't do it with fewer sticks? And that turns out to be a very difficult thing to tell. There's still a lot of 8 and 9 and 10 crossing knots that we don't know the stick number for yet. So there's a lot of open questions yet, a lot of really interesting research going on in knot theory right now. And so I'm going to stop there. I just want to be clear on this. If you get interested in knot theory, there's a couple of books out there. There's the Knot book, which is a book all about the mathematical theory of knots. And there's a comic book called Why Not, which has as its main character the superheroine there whose name is Knot Man, because she's a woman. So it's a bad pun. Anyway, thank you very much for listening.